Welcome back to this session on network analysis. So, we will continue with the ideas of network analysis that we have been talking for the last few days. So, today I will introduce two important metrics that are very useful in the context of directed networks and especially in the context of citation networks. The first one among this is called co-citation index. So, the idea is very simple, that when you look at a author citation network, the type of network that we were discussing already in the context of degree distribution studies. So, if you look at an author citation network, what you observe is that there are at times where two authors who are not connected by a citation relation among themselves have some relationship in a indirect manner, okay, and that is what we want to study here, and that is what we want to quantify in this through this metric. So, let us for instance consider this small hypothetical network here. So, from this network you immediately see that author 1 is cited by author 3 and similarly author 2 is cited by author 3, right. So, mark this word cited by. So, basically there is this author 3 who actually co-cites both author 1 and author 2. Okay. You even get a stronger evidence of such co-citation behavior when you look at author 4. We find that author 4, author 1 is also cited by author 4 and author 2 is also cited by author 4. So, this gives us additional evidence that probably although author 1 and author 2 are not connected by any citation relation, they perhaps have a relationship, okay, between themselves, and that relationship could be many things, could be in the form of that both author 1 and author 2 work in the same field. Say for instance, you can imagine that probably both author 1 and author 2 work in AI, okay, or machine learning. Okay. Also it might be the case that author 1 and author 2 work on similar topic or method. For example, say SVM in machine learning, in the area of machine learning. So, such relationships between such hidden relationships between pairs of authors or a group of authors might exist in a author citation network, and unless you have a construction, you design an appropriate construction, it is not possible to tear through these relationships, okay. And such constructions are not very difficult to formulate. For instance, let us consider that this author citation be named as A. So, let the matrix for the author citation network, this be denoted by the matrix A. Then the co-citation network is nothing but simply the product of the two matrices A transpose A. If you construct the A transpose A of this graph, then you get a new graph which would look like there will be only 2 nodes 1 and 2, and there will be an edge between them, indicating a co-citation relationship. Okay, indicating a co-citation relationship. Now, imagine that there are many such intermediate nodes like node 3 and node 4 in this example. Then the evidence that the nodes 1 and 2 share some relationship becomes stronger and stronger. Then more the number of nodes, the more the number of intermediate nodes like node 3 and node 4, the stronger is your evidence that there is some sort of a relationship, some form of a relationship that exists between node 1 and node 2. Okay. Now, likewise there can be a symmetric or a mirror image concept which is called the bibliographic coupling. So, this is, as I said, is just the mirror image of co-citation index. So, let us, to understand the concept, let us again draw the same hypothetical citation network example. It is only in the difference of how you read the citation relationships. So, in this case what you see that author 3 cites author 1. So, the earlier relationship that we were talking about was cited by, and here we are more concentrating on the relationship cites. Similarly, author 4 cites author 1. And again you have a second level evidence, a stronger evidence, making your observations far stronger, where you see that author 3 cites author 1, similarly author 2, similarly author 4 cites author 2, right. So, the earlier case was considering the cited by relationship, the current case is by considering the cites relationship. Okay. So, author 3 cites author 1 and author 4 also cites author 1, similarly author 3 cites author 2 and author 4 also cites author 2. So, this indicates that there is a possibility that authors 3 and 4 share some relationship. So, again extending the same idea as we talked about in the co-citation index context. So, basically here you are no longer considering author 1 and 2, but authors 3 and 4 who have the similar citation behavior, who have similar patterns in their reference list, okay, the similar referencing behavior. You can also call it as a referencing behavior. The way author 3 refers to papers is the author 4 also refers to papers in a similar way. Again the idea is that probably these two authors work on a similar field or on a similar topic, that is why very often they have to cite similar other people. So, there could be a relationship in that way existing between authors 3 and 4. So, this kind of a relationship is called the bibliographic coupling. Again if we consider that the corresponding matrix for this network is A, then for the citation author citation network is A, then the bibliographic coupling network can be obtained just by the product of the two matrices, but now written like A dot A transpose, whereas the co-citation index matrix could be obtained by A transpose dot A. Here the bibliographic coupling matrix can be obtained by A dot A transpose, and these two networks are used in conjunction with the original author citation network matrix to do various sorts of recommendation tasks, citation recommendation, authorship recommendation, and various other recommendation tasks that where people heavily use IR techniques, but then at the back end some of the metrics that are used, some of the quantifications that go on are basically drawn from these three networks A transpose and A transpose A. So, continuing with other metrics, we will now introduce another very interesting concept for directed networks, and this is called reciprocity. The idea is very simple. Suppose there is a node A and there is another node B in the network, and there is a directed edge from A to B. Now, as the name suggests, reciprocal means if there is a link from A to B, there is a reciprocal link from B to A. So, in directed networks there might be a link back from B to A. This is a very different link from the link from A to B in the context of directed networks. So, if there is a link from A to B, then if there exists another link from B to A, then we say that this is a reciprocation of the original link A to B. Okay. So, the reciprocation of the original link A to B is the link B to A, and the associated quantification is called reciprocity. Okay. So, the idea is very simple. So, quantification is quantification of reciprocity, which you define by the metric R, is nothing but what is. So, if you have m edges in the network, if you have a total number of m directed edges in the network, among these how many edges are actually reciprocated. Okay, that is the idea. So, if there are say if there are n nodes in the network and there are some of the edges which are reciprocated, and then there are some of the edges which are not reciprocated. So, you express the total reciprocation in terms of as a ratio of the total number of edges in the network. So, that is how reciprocity is defined. So, basically it is in the directed network Aij, Aj. So, there is one link from Ij and there is another link from Ji. If the product of these two, so if Aij is 1 and also Aji is 1, then this product will become 1, otherwise in all other cases this product will be 0, right. If there is 1 and 0, 0 or 1, in both the cases this product will be 0, only in the case where both of them are 1 that this product will be 1, and this is expressed as a fraction of the total number of edges in the network. So, m is the total number of edges in the network. So, this is how you define the reciprocity of a graph. So, the next concept that we will talk about is called the rich club coefficient. This is another very interesting phenomena. So, this is for the time being we will only consider undirected graphs, undirected unweighted graphs for estimating the Rich club coefficient. So, the idea is very simple, that given a social network or say given a collaboration network of scientists, do you find a group of people, a group of scientists or a group of nodes in the social network who are in some sense rich and actually form a dense connectivity, actually establish a dense connectivity among themselves. So, they have to be rich and they have to be densely connected. These are the two constraints that this set of nodes need to satisfy. Okay. So, basically how to quantify richness? So, richness in the context of Rich club coefficient can be quantified in different ways, but the most basic one is to assume the degree of the node. So, if the degree of the node is above a threshold say k, then you consider this node as a rich node. So, richness is in this case analogous to the degree say k of the node being considered. Suppose there is a richness threshold, say richness threshold is set to some k prime, then you consider all nodes in the network where the degree of the node k is greater than or equal to the richness threshold k dash. So, you consider all the set of nodes in this set where the degree of the node is greater than the richness threshold k prime or k dash. Okay. Now, suppose the number of such nodes, okay, with k greater than equal to k dash is some n nodes. Okay. So, now you consider this set of n nodes and you see what is the density, calculate the edge density or the density of edges in between the n nodes. Okay. So, you calculate the density of the edges in between these n nodes, which are actually the high degree nodes or nodes having crossing the richness threshold bar of k prime. Okay. So, that how will you calculate the density? It is very simple. The density is nothing but the number of actual edges between the n nodes divided by the maximum number of edges that is possible between these n nodes. So, the maximum number of edges possible is NC2, whereas you express the actual number of edges between these pairs of n nodes as a ratio of the total number of the maximum number of edges that is possible between these n nodes. Okay. And this is actually the Rich club coefficient of the network being considered. So, you can imagine as soon as I talk about this, you can very well imagine that the Rich club coefficient is nothing but trying to express whether the nodes which are rich in terms of say degree, whether the nodes that are rich in terms of degree have a very high number of connections among themselves. So, basically for instance, take for the example the actor-actor network, okay, from the movie actor example that I have cited earlier. So, the actor-actor network here, if you find a rich club, this would mean that the most influential actors, okay, packed together form a clan with each other, from a group with each other and sign movies together, so that the next movie release is really a box office hit. Similarly, there quite often we have found that in the scientific domain there are a bunch of scientists who are really very highly cited and very highly popular scientists. They come together and do something very impactful, something very seminal. So, whenever such a seminal thing happens, there are a bunch of highly well known, well established scientists, they come together, form a rich club, and by virtue of forming this rich club publish something very seminal, like for example, in the current last 1 or 2 years context, one of the examples would be this Hadron Collider and the idea of God particles, which you have probably come across in various news articles. Now, the next concept that we will talk about is the entropy of the degree distribution. So, this is another interesting idea. So, very simply put, so we if you recollect, the degree distribution is encoded in the variable pk, which is nothing but the probability that a node chosen uniformly at random has a degree k. So, this was what was the idea of the very simple idea of degree distribution. Now, one can, since this is a probability distribution, one can always estimate the entropy of this distribution. So, simply put, the entropy H is nothing but Pk log Pk, and as you can well imagine that entropy actually encodes the randomness, okay, the extent of randomness in a distribution. So, this if this quantity is high, then the distribution is relatively random and the network structure is also relatively more uniform, whereas if it is skewed, if it is lower, then probably it is not the case. So, some examples could be, some interesting examples could be like, some interesting exercises could be like, what should be the entropy of Pk for, let us call this Hpk, okay, the entropy of Pk, that is Hpk for a regular graph. So, a regular graph is a graph in which all nodes have the same degree. Okay. So, a clique is also a regular graph where each node has a degree n minus 1, where n is the total number of nodes in the network. So, similarly, if in a network each node has a degree k, then that network is called a k regular graph. So, basically in such a system, in such a network, what do you have? Pk is 1 for that particular value of k for which you are constructing the regular graph, and Pk is 0 for all other values of k, right. So, in such a case, what should be the entropy? It is very simple to find, right. So, you can easily compute the entropy. So, for that particular value of k there will be, so it is, that is 1, Pk is 1 log 1 plus the rest is, there is nothing. So, such a network does not encode any diversity, that is what is being actually talked about. So, in such a network you do not observe any diversity, all nodes have similar degree. So, that is why the entropy goes to 0. Whereas, if there is a network where the degree is way skewed, then the entropy is more close to non-zero values. Okay. So, that is the idea of measuring the entropy on top of a. So, this again gives you an idea of the topological structure of the social network, underlying social network. So, one is the degree distribution itself, and on top of it you can also measure the entropy of this distribution to understand, to get an idea, better feeling. So, suppose if the entropy of such a network is close to 0, then you immediately get to know that this is a more sort of a regular structure, whereas if this entropy is not close to 0, then it is a more non-trivial structure that is there in the social network. So, and there is this last concept that we will get introduced to, which is called the matching index. Okay. So, basically what this matching index tries to say is, tries to quantify is that how similar are two nodes in terms of their in terms of their connectivity patterns. So, the matching index mu ij is actually expressed using the following formula. So, as soon as I write the formula, it becomes very clear to you. So, what we are trying to see, suppose there are two nodes I and j in the network, and there is some other node k sitting out here. Okay. So, and we assume that there is already an edge between I and j. So, basically if there is a lot of connections like k, say there is some k prime, say there is some k double prime, all of this actually connect I and j. Okay. So, these k prime, k double prime, k are the number of nodes that is being measured by the numerator of this formula aik kj. Okay. So, basically you are trying to count how many such triangular shapes or triangle completions exist between I and j, and that you express as a fraction of the sum of the degrees of I and j. So, basically this gives you an idea of the balance. So, if there are two nodes I and j and there is an edge between them, and if everything, all other connections, all other nodes, all other intermediate nodes between I and j, there is a connection from actually I to k and k to j. If the structure is like that, there is no other node other than this set of k values, then the matching index is maximum. Okay. Now, if there are many other nodes which like, so basically it might be heavy on I, there may be a high number of nodes, high degree, I might have a very high degree, similarly j might have a very high degree. Okay, but the overlapping set of nodes is not so high, then the matching index is low. So, basically you see how well is the match between the neighborhood of I and the neighborhood of j, how balanced is this match, that is what you try to quantify using the matching index. Okay. So, we stop here.